Hello everyone, this is Devabroto and welcome to our channel Schrödinger's Cat. Previous we discuss the superconductivity of the chapter on dense matter physics, and today's class we will discuss the bipolar junction transistors. And basically here the chapters are the transistors operation and configurations, DC biasing, BJT, fixed bias circuit, emitter-stabilization bias circuit, voltage divider bias with 3-part Q points, transistor saturations, load line analysis, and last one is DC bias with voltage feedback. And basically the total number of questions are coming in electronics in IIT JAM. There are 9 to 10 questions. For JEST 5 questions and TIFR 3 questions, CSIR net 5 to 6 questions, and for GATE 4 to 5 questions, and from BJT or transistors there are coming already at most 2 or 3 questions per year. So we just go ahead our next discussions, that the transistor configurations. Basically that transistors is a 3-layer semiconductor device consisting of emitter, 2 N and P type layer of material of 2 P and 1 N type layer of the material, and this is called NPN transistors. With diagram shows here that this is for basically NPN, and basically this would be the minus and this, and basically we have that the collector here and IC, and here IE, the emitter, and E here, that would VEE and VCC, negative to positive terminal, and basically the NPN. And for transistor configurations we have basically PNP and NPN configurations. That first one for the PNP, just this one and this is basically emitter, collector, and another one is base, and here from the current IE, here IC, and another one IB, and basically E to B for PNP, and another one for NPN, that would like that here this one is emitter, collector, and base, and B to E. So basically NPN transistors. And input characteristics is basically would like to have this graph for IE in millivolt, and this is origin, and another where is voltage BE in volt, and the output characteristics basically that this one, that one, another one. This is basically IC in milliampere, and that one is VCE in volt, and this one is basically origin, and this region is in cutoff region, and that one is active region, that one is active region. And basically here we have some configurations like that, and after one we should go here that for this one is for CB mode, and another one is basically C configurations. That one, that CE. So here that this one, so basically here the base and the collector and the emitter and the base to emitter, this current flow for NPN and for PNP, that this one, and this is basically C emitter and the base, and current would flow from emitter to base. This is for PNP. And here one equation is important, that the IC is basically alpha IE plus ICBO, is for alpha common here, IC plus IB plus ICBO is basically IC would get here alpha IB by 1 minus alpha plus ICBO by 1 minus alpha, and that would become the IC is equal to beta IB plus ICEO, and basically or ICEO would become ICBO by 1 minus alpha at IB equal to 0, and for beta equal to alpha by 1 minus alpha. This is the relation between the alpha and the beta, and we have defined two parameter here, that for the important C, that alpha DC is basically IC by IE, and that one, that the IC is equal to alpha E plus ICBO, and the another one, the basically alpha AC mode, that del IC by del IE for VCB is equal to constant, and where alpha is called the common base short circuit amplification factor, and the voltage amplification would become V0 by Vi, and the current amplification would become IE by IC, IC by IE, current amplification and voltage amplification. And another one is that the beta configurations here, the beta DC, that the beta DC here, beta DC would become IC by IB, and the beta DC for constant VE, that del IC by del IB, basically for the VCE is equal to constant. Here beta is called for the C mode, here the common emitter forward current amplification factor, and the another one is the for the CC mode, here that would be like to in the form of CC mode, that basically this one, and here would become emitter, and this is for C, and D2 would be V, and the emitter to base current flow here, and it is for the PNP. And for NPN transistors we should get here the emitter and the collector and the base. Here current flows from the base to emitter, and here is a factor is called the gamma. Gamma is basically I by IB, emitter current with ratio to base current, and the alpha is basically, we should prove here, beta by 1 plus beta, and beta is equal to alpha by 1 minus alpha. Alpha beta and gamma relation, gamma would become 1 plus beta, and gamma to alpha is basically 1 by 1 minus alpha, and where the ratio would become alpha less than beta less than gamma. So basically in the CC mode here, and we just configuration of CB, CE and CC mode we just discuss here, and we just go through the DC biasing of BJT. The biasing, we have the DC biasing and the emitter stabilization bias and the voltage divider bias and the DC bias voltage feedback. First of all, we just discuss here the fixed bias circuit, and after one DC biasing BJT. So basically in the DC biasing BJT, that here one thing is that for numerical problem solutions, that keep in mind VBE that becomes 0.7 volt, and the I emitter current that would beta plus 1 IB that nearly equals to collector current, and the IC is basically beta IB. And one thing is that for linear region operation, that the base emitter is in the forward bias and the base collector would be the reverse bias. For cutoff region operation, that we get here that base emitter is in the reverse bias and the base collector is in the reverse bias, both are in the reverse bias. And the third one is the saturation region operation. That would become the base emitter is in the forward bias and the base collector is in the forward bias. So basically we have discussed here the DC biasing of BJTs, and the another topic is the fixed bias circuit here. For the fixed bias circuit, we should have drawn the circuit for simplifications, that here the transistors, and these are the modes of, this is basically one end and another one, and this is, and that's joined here, and this one is for V, and here is basically input AC, and basically this one is output AC. So here we just to have find that here this one is plus and minus, here it is the emitter, it is the base, and the collector one would be the C, and here this region is VBE, and that one is plus minus VCE, and basically here it is the RC collector regions and the base resistance, and joined by the VCC, and the current flow through it their IC, and this one is the IB. This is our block diagram and the circuit diagram for the fixed bias method. And for fixed bias method, we just KVL apply here for a loop. We just get here plus to minus is basically the minus VCC plus resist voltage through it IB RB, and plus V B should be 0, and basically for the base current would become VCC minus VB is divided by RB. And for the collector emitter loop, we just get here that the IC is nothing but the beta IB, and this is for the forward bias of the base emitter, and that one the collector emitter region. This is for the collector emitter region, that IC is equal to beta IB. And we have another thing to discuss here, the load line and the Q points. Basically for the load line, we just draw a graph, input characteristics here, This is for the VCE and that on the origin, and that is the IC. The output characteristics of the transistors just look like that. So basically here a straight line drawn here, and this point is VCC and this one is the VCC by R, and this is VCE at 0 volt, and this one is IC for 0 milliampere, and basically this point is known as the Q points. And here we just, for the load line concepts, VCE is basically VCC at IC is equal to 0 milliampere, and the IC is equal to VCC by RC at constant VCE collector to emitter, that 0 volt, and this gives a straight line is in the form of VCE equal to VCC minus ICRC. Basically the straight line is called the load line, and from here we just get the load line concepts and the Q point concepts. And basically we just now go through the another part, that emitter stabilization bias. Basically for the emitter stabilization bias, that we should first draw the circuits of emitter stabilization bias. That is basically, this is the transistors here, and this regions is in the base of this RC, and this one and this one, and this one a point is goes here, and this is another resistors. So basically this one C1, C2 input voltage, output voltage, this one is RE, this one RC, RV, and basically the VCC, and the here the current through it basically the IV, and here that the IC currents, and here the IE emitter currents, and basically it should be ground here, and the current flows must be the base to emitter region. That fine. This is our emitter stabilizations, and here we just apply here the KVL in the loop here, that base emitter loop analysis. We just get that plus to minus VCC plus IB RB plus VB plus IE RE is equal to 0. So minus should be common here, VCC minus, or VCC minus IVRV minus VBE minus beta plus 1, just put the value here and the get IVRE is equal to 0, where we just put the value here that IE is equal to beta plus 1 IB. So now we just get the base current IB is nothing but VCC minus VB is divided by the RB plus beta plus 1 into RE. This is our base current, and we just analysis the collector emitter loop, collector emitter loop discussion, that gets the value of that basically the IE RE plus VCE plus ICRC minus VCC is equal to 0, and here we assume IC is nearly equals to IE and VC equal to VCC minus IC is common and the RC plus RE. So third one is the saturation loop, and the saturation levels. For saturations level we just get IC sat is nothing but VCC by RC plus RE, and these are the emitter stabilization conditions. And now we will just discuss here the voltage divider bias. This is very important for the exam purposes. That's very important thing is that voltage divider bias. Basically for voltage divider bias we have the circuit here. This is basically the transistors and this one, and this resistance and this capacitance, and that one is another capacitance connected through here. This one is connected this, and this one is a resistance connected, and here would be the VCC. So basically that V input, V output, C1, C2, main thing is that current flows in this directions here, and the R1, R2, this is the RC, this is the RE, and this is VC. So basically here for deducing this formula, first of all we just here Thevenin's resistance R1 and R2 that get RTH R Thevenin is basically R1 R2 by R1 plus R2, and the second one is Thevenin equivalent voltage is basically the VR is nothing but R2 VCC is divided by R1 plus R2. This is our key concepts, and we just mesh analysis in a loop, and using the KVL we just get here that minus E Thevenin plus IB in these loops, IB RTH plus VBE plus IERE is equal to 0, and the IB base current would become ETH minus VB is divided by RTH Thevenin resistance plus beta plus 1 into RE, because we just consider here that the IE is nothing but beta plus 1 into IB, and this is our, and the another one is the collector analysis. We just get VC is basically VCC minus IC into RC plus RE. By the we just apply KVL, there is nothing to do here. And the another one is discussed the last topic here, the voltage feedback, basically the DC bias voltage feedback, and that would become the circuit here, that this is the transistors here, and the another part, this one is a resistance, and voltage feedback should become that one is feedback to this is output, so it's called the bias feedback, and basically it is RC, and this one is IC dashed, this one is IC, this is here is the IE, and this is plus to minus is basically the VCE, and this is the RE and RB, and C1, this one is called the, this one is feedback. So basically we just again in the mesh analysis do KVL and base emitter loop, that the base emitter loop we just get here that VCC plus IC dash RC plus IB/RB VBE plus IE/RE is equal to 0, and get IC dash is basically the IC plus IB is equal to IC. And for the collector loop, we just consider for the collector loop that the VCC minus beta IB RC minus IB into RB, just positive to negative, that's negative VCC, negative to positive, that minus B. Sign convention of this KVL form, minus VBE and beta IB/RE, that would become 0, and we get the base current here VCC minus VBE is divided by RB plus beta RC plus RE. This is our final outcome. And when we just consider the collector emitter loop, that minus VCC plus 2 minus plus IC dash RC VCE plus IE/RE would become 0, and get collector to emitter voltage is basically VCC minus IC common, and get RC plus RE. This would be our theory, and we just discuss in shortly the some bias method of the transistors, and here we just not elaborately discuss the theory. We should just go at our entrance exam like JAM, JEST, NET, GATE, TIFR. For that point of view, we just some theory, and after one we just go ahead our problem discussion class. That the first problem is coming in NET June 2017. It says that in the N channel FET shows the figure below, that the basically Vi minus 2 volt and the capacitor is 10 picofarad, and the VDD drain to drain voltage is basically 16 volt, and the RD drain resistance 2 kilo ohm. If the drain D source is saturation current IDSS is 10 milliampere, and the pinch off voltage VP is minus 8 volt, then the voltage across the point D and S would become. You just try, and I just explain these problems. So this one, the circuit, the JFET, G, S and the D, source and the drain, and this is the output and input. Just like as the some biasing method of the BJT here, and here the value given that voltage of VSQ is nothing but VGG is equal to minus 2 volt given, and we have the formula IDQ is basically IDSS 1 minus VGS is divided by VP tar whole square. So basically it would become to value 10 1 minus 2 here, put the value, and here minus 8 whole square, and after numeric calculation we just get 5.63 milliampere. And here we should find the VDS, basically the VDS, that VDD minus IDRD. We just discussed this theory. VDS, basically this term is VDD plus 2 minus ID minus RD, because we just this loop KVL apply, and after one we just put this value 16 here minus 5.63 RD value 2, just calculate and get the result 4.8 volt. So basically 4.75 nearly equals to 4.8. D would be our correct answers. Go ahead our next problems coming IIT JAM. Basically the value of emitter current in the given circuit is what microampere. This is our circuit here, you just look upon, and we discuss this circuit emitter biased method, and you have to find the emitter current I is what. Basically that the relations we now deduce that IB VCC minus VB we just derive by mesh analysis in the KVL apply RB beta plus 1 RE, and that would become the value 10 here, and VB is 0.3, this is given 0.3 volt is divided by 2 into 10 to the power 6 plus beta plus 1, beta is nearly equal to 100, so 101 is into 2 into 10 to the power 3, so it would become 9.7, and this calculation is 2.202 into 10 to the power 6, and we have to find the emitter current, that would become the beta plus 1 into IB, this is our formula, and that so 101 into this, put the value 9.6 2 point, just a minute, 2.202 into 10 to the power 6, this is for 444, you just do calculate in your calculator in 0.9 microampere. So what microampere, this is IIT JAM NAT type questions, 2 marks, our value would become 4.9. so we just here discuss the most important questions coming in IIT JAM, JEST, CSIR, NET, GATE and TIFR also, these 5 type of questions, and after doing this you just do all the questions in coming in the national level examinations, and for better understandings I just give you some problems relating to this. So here coming the TIFR questions, that saying in the transistor circuit shown on the right, assume that the voltage drop between the base and the emitter is 0.5 volt. What will be the ratio of the resistance R2 by R1 in order to make the circuit functions as a source of constant current I equal to 1 milliampere. So basically this is the transistors and load to resistors, and this one is RE. Basically we have to find the R2 by R1. Here given that the collector current is equal to 1 milliampere, nearly equal to emitter current. Because collector current is very much light and the base voltage is become the IE RE plus VB. Just do the KVL in this loop, put this value 2 plus 0.5 equal to 2.5 volt. Now VB would become R1 VCC divided by R1 plus R2. This two resistance junction voltage would become this, and we just get here the R1 plus R2 divided by R1 is basically 3. After calculation we get R2 by R1 is nothing but 1 2. So D would be our answers. Go ahead our next questions. JEST. Coming in JEST, consider the transistor circuit showing in the figure. Assume V VEQ is 0.7 volt, VBE is 6 volt, and the leakage current is negligible. What is the required value of VB in kilo ohm in the base current is to be 4 microampere. This is coming in JEST 5 marks questions, numeric type. So here we just apply KVL in this loop, this one is, and these two loop we apply in every problem, that minus VBB plus IB RB plus VBE would be 0. So basically we get RB, the VBB minus VBE is divided by RB. Put this value 6 minus 0.7 divided by 4 into 10 to the power minus 3, that would become 1325 kilo ohm. So 1325 would be our numeric answers for the JEST problem. Just apply KVL in the two mesh. We just do here the mesh analysis, these loops, final problems coming in gate, that saying for the transistor amplifier circuit shown below with R1 10 kilo ohm, R2 10 and R3 is 1, beta 10 is to 19, neglecting the emitter diode resistance, the input resistance of the amplifier, looking into the base for small AC signal, what would be the value of this input resistance. Basically we just find here the ZI, input resistance for small signal. This is the R1, R2 and R3, and that would become the voltage divider bias, and we just discussed earlier basically that the ZI solution would become ZI, that ZB base impedance parallel to R dash, where the ZB nearly equals to beta R3, this one is R3 or RE. So it is given the 99 kilo ohm, and this one is R1, this would become R1, and the R1 is basically R1 parallel R2, R1 parallel R2, this R1 R2 parallel, we just become the R1 R2 by R1 plus R2, basically 10 plus 10 20, so 5 kilo ohm, and the final outcome that the input impedance is ZB parallel R1. So ZB parallel R1, we just get the value ZB 99, parallel R1 is 5, so 99 into 5 by 99 plus 5, we just get value 4.75 kilo ohm. So what kilo ohm? This is gate NAT type questions, 2 marks. Our numerical answer would be become 4.75. So basically we just conclude that conclude the problems, and I usually do homework for better understanding and practice. So we have just solved 5 important problems coming in IIT JAM, JEST, NET, GATE and TIFR also, and I just do some homework. This one is the first, you just do it and mail me. A silicon transistor with built-in voltage 0.7 volt is in the circuit shown in the figure with these values. Which of the following figures correctly represent the load line and the quiescent Q point we just discuss for the IC versus VC output characteristics, the load line, the straight line equation and the quiescent point. You just try to solve, just pause the video and take a screenshots. So second one is in the diagram, and the NPN transistor giving this value, you just calculate R1 by R2. I just also solve in the TIFR problem this type of questions. You just pause the video and take a screenshot also. Third questions, that this is a circuit and this is value NPN transistors, and we have just find that DC base current in microampere. Also pause video and take a screenshots. Next problem for homework, this is a transistors and this value, you have to find that V output should be find. Last but not the least, that this is also transistors combining with op-amp, we have to find the base current. This is a tricky questions, I should it coming in the IIT jam. So basically, pause the video and take screenshot of the 5 questions you just do in your homework. So here we just solve 5 important questions and give home tasks for a better understanding and practice 5 more questions. So you have already practiced and 10 questions important in national level examinations. So we just here just do discuss the brief theory, not in elaborately, and do some problems for the entrance examinations, and after we should just get time and we should discuss derively the theory for a better concepts, and you just do the 5 home tasks according to 5 that I usually practice in these lectures, and this remain 5 you just complete and mail in this ID catschrodingers1935@gmail.com. So solve this homework, and if anyone need the files like study material of my YouTube lectures, just mail in this ID. So thank you, stay happy and goodbye, take care.